Dude, if I build a quartermaster here to defend my settlement, I would lose out on so many resources. But instead, if I build a marketplace, I would gain a lot of resources. But this Noxian army next door would probably attack my settlement and destroy it. What do I do?
Ah! Hi, are you trying to use computer science and/or mathematics to optimize your video game decision making?
Well, yes, but wait, who are you?
Who am I? Well, none other than the prestigious Pi Professor, of course, or Triple P for short.
How did you get in my computer?
I'll ask the questions, please, and thank you. Have you considered writing some code to solve this critical problem?
Well, yes, I did write some code that's partially brute force and partially greedy, but it only works because the graph size and order is really tiny, and even then it takes ages to run on my laptop.
Ah, I see. Well, in this case, we will have to resort to using some advanced mathematics to solve our problem. What exactly are you trying to achieve?
Well, I have all these settlements in my kingdom. You can think of the settlements as vertices, and they are connected by roads, which you can think of them as unweighted, undirected edges. But I only have a limited number of structures to build in each settlement, and I want to make sure my settlements are well defended.
Let me guess. You want to use the Raptor Aviary structure, which defends the closed neighborhood of whatever settlement it's built in, right?
Yeah, but I don't want to build too many Raptor Aviary structures, because then I would be losing out on very important resources like wood, food, and iron.
It sounds like you're trying to determine which settlements to build aviary structures in, such that the number of edges connecting aviary-equipped settlements and non-equipped settlements is maximized.
Yes, exactly. How did you know all of that? You are so smart, Triple P.
Indeed I am. And you know what? This is a famous problem in graph theory, and it's called the max cut problem. Let's get straight into it. A cut C is simply a partition of vertices into two disjoint subsets S and T. The cut set of C is the set of edges that have one vertex in S and another in T. In an unweighted, undirected graph, the number of edges that cross over from one subset to the other is the size of the cut. Our goal is to find the maximum cut for any given graph G, which is the cut whose size is greater than or equal to the size of any other cut. This problem is NP-hard. In other words, there are no known algorithms that solve this problem quickly enough for any graph G of arbitrary order or size. Therefore, we will showcase the Gomans-Williamson approximation algorithm, which guarantees we arrive at a cut whose size is at least roughly 87.8% of the theoretical max size. For any cut C, let's consider the following expression, where for all edges u, v in G, xu and xv represent which side of the cut each vertex is in. In general, if xi equals 1, then vertex I is in the S half of the cut. If it's equal to -1, then the vertex is in the T half. Consequently, summing over all edges of G, the following sigma expression is equal to the size of the cut. We shall now maximize this sum. Let's expand the binomial in the sum, and for each vertex I in G, let's represent xi with a corresponding one-dimensional yi unit vector instead. We can do this because xi is always either 1 or -1 for any vertex. As a result, we can now turn the expression under sigma to a sum of dot products. Since there are n vertices in our graph, our y vectors will span a space equal to r power n at max. Therefore, they can be visualized as vectors placed at the center of a unit hypersphere in an n-dimensional space. We will visualize this with a 3D sphere for simplicity, and in a moment we will figure out which direction to choose for each of our y vectors. Since our y vectors are unit vectors, we know that for any I, yi.yi equals 1. Using this to simplify our expression, we now have it in a format where we can borrow a method from computational linear algebra known as semi-definite programming. We use this method to optimize the directions of our unit vectors and find our cut. The core idea behind the process is to place vectors for adjacent vertices such that they are looking in opposite directions as much as possible. The final step is to choose a random hyperplane that passes through the origin and slices our hypersphere in half. Vectors in the first half of the sphere represent vertices in the S half of our cut, while vectors in the second half of the sphere represent vertices in the T half of the cut. This is why we wanted adjacent vectors looking in opposite ways, to maximize the probability that they end up on different halves of the randomly chosen plane, making it more likely that adjacent vertices would be put in different halves of the cut, and thus maximizing the size of the cut. In fact, the probability of any two vertices being placed in different cut halves is directly proportional to the angle between the two vectors representing these vertices. If we rewrite the expression denoting the expected value of the cut size using some trigonometry, and then use the first and second derivative tests from Calculus 1, we will find that the minimum of this expected value is at least 87.856% of the theoretical max cut size.